So one of my viewers was asking me to show them a practical example of modified unit analysis, MUA, or MOA for short. Coincidentally, someone else sent me a paper with the perfect practical example to demonstrate my logic, or the logic of MOA. The paper is called Measuring the Momentum of Light by Christopher R. Jacobson from the Niels Bohr Institute in Denmark. So let's read this. In physics, momentum is one of the most fundamental properties. The law of conservation of momentum is universal. According to the special theory of relativity, light has momentum despite the fact that a photon has no mass. This claim is very surprising. For how can something without mass have momentum? From Newton's second law of motion, we know that something that has momentum can exert a force. So can light exert a force? And if so, can we measure it? Well, we know that light does exert a force, but how does light exert a force if it doesn't have mass? Using the standard definition of mass, this seems paradoxical. It is my opinion that the concept of inertia and mass is ill-defined in mainstream physics, and that is the source of the paradox. Modified unit analysis defines things a little differently in order to remove any ambiguities in the language. MUA decouples the concept of inertia from the concept of mass and defines them as follows. In MUA, inertia is simply defined as resistance to change. This is the only definition of inertia required by MUA. And mass is defined as a quantity of matter. This is the way mass is defined in chemistry, and so MUA adopts this definition. A 1 kilogram mass of copper, for example, is a quantity of matter occupying a volume of space. The term mass is confusing and ambiguous in standard physics because it has two definitions. It is a quantity of matter, and it is matter itself. MUA decouples the concept of mass from the concept of matter and defines them separately and non-ambiguously. Of course, now matter needs to be defined. But first, let's deal with inertia. The definition of matter will fall out of the definition of inertia. Modified unit analysis defines two kinds of inertia. The first is potential inertia, with units kg. This is what we traditionally call mass. This is the first half of Newton's law of motion. An object in stillness remains in stillness unless acted upon by an external object. An object in stillness resists change to its state of stillness. This is what we normally call rest mass. An object in potential remains in potential unless acted upon by an external potential. The second form of inertia is kinetic inertia, with units kilograms meters per second, which are the units of momentum. In modified unit analysis, the capital P in the unit section is used for the unit of momentum. This is the second part of Newton's law of motion. An object in motion remains in motion unless acted upon by an external object. An object in motion resists change to its state of motion. This is otherwise known as momentum. In MUA, stillness inertia, or potential inertia, and kinetic inertia, or momentum, are two forms of resistance to change, or inertia. In terms of the principle of incommensurability, defined by MOA, these two terms, potential and kinetic, are incommensurate principles. Light and matter are incommensurate principles. Light is not matter, and matter is not light, but together they form a conjugate relationship such that without matter, light cannot exist, and without light, well, nothing matters. Matter, when not in motion, can be thought of as pure potential inertia. And light, which is always in motion, until it bumps into an object, of course, can be thought of as pure kinetic inertia. In reality, though, due to the conjugate nature of light and matter, there is no such thing as pure potential inertia, and there's no such thing as pure kinetic inertia. It is always somewhere in between. So light, although almost completely potentialless, has a tiny potential. As well, there is no material object in the universe that is not in motion. In other words, only momentum exists in nature because light is always in motion and matter is always in motion. In fact, conservation of inertia, which encapsulates conservation of matter and conservation of momentum, is the only conservation law defined by modified unit analysis. All other conservation laws fall under and/or are a result of conservation of inertia. So in light of the definition of inertia in MUA, pun intended, it is not so surprising that light has momentum, because light, defined as pure kinetic inertia or nearly pure kinetic inertia, is in fact momentum by definition. Light defined as pure kinetic inertia or nearly pure kinetic inertia is momentum by definition. And this is the starting point for the practical example that is described in this paper. In fact, I ended up writing my own paper, which I will link in the description, which shows how I use modified unit analysis to solve this problem. So here's the problem. Given a 0.516 watt laser emitting a light with a wavelength of 726 nanometers, what force would the light emitted from such a laser exert on an external object? In standard physics, the following equation might be used to calculate the force. Force is equal to power over the speed of light. Now this equation is just a first order prediction which assumes that the object is a perfect reflector and does not account for other effects such as energy absorption or heat, which can result in other forces. So this paper measuring the momentum of light actually does deal with some of those other situations. But in an ideal situation, this equation would be used, and this is the number we're looking for. Then I go on to do a quick review of my other paper, Planck's constant and the nature of light, which I also made a video on. Using modified unit analysis, MUA or moi, and the logic outlined in a previous paper, Planck's constant and the nature of light, this exact value will be deduced from first principles. Although this derivation is not as elegant as the above equation, it serves the purpose of corroborating the MUA interpretation of light, which differs significantly from the standard interpretation. In the MUA interpretation of light, each oscillation of light carries the same energy, and now I'm saying it also carries the same momentum, no matter what frequency we're talking about. Higher frequency light has a smaller footprint, and so the same energy and the same momentum is hitting a smaller area of the detector in a shorter period of time. As well, more energy units, more oscillations, are entering the detector in unit time, or 1 second, than the lower frequency light. Both of these effects contribute to the fact that higher frequency light delivers more power and or exerts more pressure, power and pressure, on an object than lower frequency light. Regardless of whether the detector receives one oscillation or many oscillations, higher frequency light, smaller wavelengths of light will deliver higher intensity, a higher intensity impulse than the shorter wavelengths of light. So what I am saying here does not contradict observation, and this is not a new effect. This is the old effect, only I am explaining it differently. Different wavelengths of light do not carry different energies. However, smaller wavelengths of light do deliver a higher intensity signal to the atoms in the detector. They enter a smaller area of the detector in a shorter period of time. This does not contradict wave-particle duality. In fact, it supports it. Instead of light, let's imagine that these boxes are full of matter. Each box contains the same quantity of matter, that is, they all weigh exactly 1 kilogram. And let's say that they are traveling towards a wall on the right at a constant velocity. The box on the top is filled with feathers, and the box on the bottom is filled with uranium. Not to scale, of course. Both boxes contain the same energy, and both are moving at the same speed. Which one is going to hit the wall with a higher intensity? I am merely saying the same thing for light. MUA refers to this as wave-particle unity. So getting back to the paper, here is my review on my treatment of Planck's energy equation. Modified unit analysis, MUA, adds the domain of oscillation as a base domain of the system along with the domains of time, space, mass, which I now call inertia or potential inertia, and charge. Using MUA, Planck's energy equation is expanded to show the previously hidden terms in the equation and associated units as follows. Here Planck's constant, h, is expanded to include the previously hidden measure time, whereby h equals what I'm calling now the cycle of energy times some measure time. The Tm parameter is then assigned to the unit s, so this extra s from the action constant is assigned to the new measure time. Now, I want to make it clear that I'm not adding an extra time parameter to this equation, otherwise I'd have to add it to both sides. Okay, this time parameter is already there because it's in the units. And this is the problem I have with a lot of physics, is equations can hide things. There's a lot hidden in this equation. Okay, equations can hide things, but unit analysis can't hide things. You can't run from unit analysis. So I know that this s from the action constant belongs to some time variable, and so I make h equal to quantum of energy, or one cycle of energy, times some measure time. Okay, in MUA, measure time is decoupled, so that's what I'm doing. I'm decoupling from the action constant. I'm decoupling this time parameter, and both in the unit section and in the body of the equation. So I'm pulling this time parameter out of Planck's constant, which is already there. I'm not making it up, it's there, and putting it into the equation. In the above equation, the term H triangle is numerically equal to 6.626 times 10 to the minus 34, or Planck's constant, but has units joule per cycle. Joule per cycle. Also, it should be noted that in this equation, the Tm parameter is numerically equal to 1 and corresponds to a 1 second measure time of the experiment. Technically, the above equation can be written as follows. Okay, this is true because all light frequencies are reported in cycles per second, with the second corresponding to exactly 1 second and not some other measured time. For example, the frequency of a gamma ray is in the order of 10 to the 19 cycles per second. And this is hertz. Since light frequency is reported on a per second basis, the measure time parameters must also be set to 1 second. Although some may be tempted to cancel the two Tm parameters in this equation, okay, or they might want to try to cancel these two ones in this equation, okay, this would only serve to hide the 1 second measure time parameter, yet again obscuring the true nature of light. There's another good reason to keep both these measure times in the equation, and I will explain this shortly. The above equation is then transformed into the power equation by dividing both sides by Tm. Okay, this is precisely why MUA doesn't cancel the two time parameters in equation 2 in this equation. Since the original black body experiments were reported in terms of power, watts per meter squared, or intensity, doesn't it make more sense to write Planck's energy equation in terms of power? The standard equation, E equals hf, actually prevents us from writing the equation in terms of power because the 1 second measure time parameter was hidden in the action constant. Okay? As you will see, writing this equation in terms of power allows us to solve the above problem in a more logical and intuitive fashion. Using a similar logic, a similar treatment is given to de Broglie's momentum equation as follows. Okay, in MUA, P is the label for the unit of momentum. Standard unit analysis, SUA, does not have a unit label for momentum. It only has a unit label for force, or the Newton. This is a small flaw in the language, but is corrected in modified unit analysis. In MUA, the units of force are written as momentum per second, instead of kilogram meter per second, or momentum per second, which equals the unit of the Newton. In a similar manner to the treatment of the energy equation, the above equation is then converted to a force equation by dividing both sides by measure time. In the NIST standard, this value, 2.2102189 times 10 to the minus 42, is assigned units of a kilogram and is referred to as the inverse meter-kilogram relationship. This makes no sense. This makes no sense. In standard units, even using standard units, H over C, which evaluates to 2.2102189 times 10 to the minus 42, H over C has units kilogram times meter and not kilogram. So even in the standard units, this does not evaluate to kilogram. So this must be a mistake. This must be a mistake. In MUA, this value has units momentum per cycle and interprets as 1 cycle of momentum, or in previous papers I called it the quantum of momentum. okay, but I'm still trying to define the language, and so right now I call it 1 cycle of momentum. Or it can also be thought of as a quantum of force. So I also use that term, quantum of force, for this value. There's a distinct similarity between this equation and equation 4, as I will show you. These two equations look very similar. One is in terms of power and one is in terms of force. Each of these equations has a quantum parameter, which I'm referring to as the quantum of power in this equation and the quantum of force in this equation. Both of these equations have a frequency term, and the units look very, very similar. So this is what I was talking about earlier, about how each wavelength of light carries the same quantum of energy or quantum of power, 1 cycle of energy and 1 quantum of power, and each wavelength contains 1 quantum of momentum, or 1 cycle of momentum, or 1 quantum of force. So this is what I'm going to use to solve the problem that we're talking about in this video. So here are those 2 quantum constants without all the junk. And now we're going to solve the problem. First, we convert from the domain of per cycle to the domain of per second by converting from wavelength to frequency using this equation. A 726 nanometer wavelength is 7.26 times 10 to the minus 7 meters. Okay, so we're using the SI units here, and so I had to convert to meters. And then we use this equation to calculate the frequency of the light. Not only is the equation F equals C over lambda a conversion from wavelength to frequency, in modified unit analysis it's also seen as a transformation from the domain of per cycle to the domain of per second. Equation 9 therefore transforms the problem domain from the domain of per cycle, or the domain of wavelength, to the domain of per second, or frequency. Next, we calculate the non-amplified power. That is the power as if the light that was being emitted was not a laser. Okay, so the laser has a power of 0.516 watts with units joules per second. In MUA, the non-amplified unit of power, or PS, in the domain of per second, is calculated by multiplying the frequency of the light by the quantum of power, this value here, which is historically said to be Planck's constant. So you multiply that by the frequency and you get this value. In MUA, the numerical value, 2.7, this value here would be normally historically interpreted as the energy of a photon. But in MUA, it interprets as a unit of power. That is, it is the continuous energy delivered over a 1 second time interval. Using MUA, the units of the above equation, this equation, evaluate as follows. So in modified unit analysis, the units evaluate to the watt, as specified up here. Next, we calculate the non-amplified force. This is the force exerted by the non-amplified light, the light as if it wasn't a laser. It's calculated by multiplying the frequency, multiplying the frequency by the quantum of force. So we're doing exactly the same thing, but instead of multiplying by quantum of power, we're multiplying by quantum of force. And we get this value. Okay, using modified unit analysis, and remembering that P is the unit of momentum, the units of the above equation evaluates as follows. As you can see, this evaluates to the unit of force. So this is a force term. Next, we're going to calculate the amplification factor of the laser. Laser literally stands for light amplification by stimulated emission radiation. Okay, so using the power term from up here and dividing by the unit of power, which is the non-amplified power that the light would have had if it wasn't a laser. So we divide the power, the actual power, by the reduced power, and we get this value. So this is the amplification factor of this particular laser, and it is quite large. This is quite a strong laser. Okay, using modified unit analysis, we see that this is a unitless value. So it is literally just a amplification factor. Finally, we calculate the actual force exerted by the laser by multiplying the unamplified force, which is here, by the amplification factor, and we get this value. Okay, and we see that we get the exact same value that we get when we use this equation. Only we came to this value using the logic of modified unit analysis. So in the macro world, most of the useful equations are written in terms of force and power. For example, Newton's law of gravitation, Coulomb's law, Lorentz force, F equals QV cross B, and electrical power, power equals voltage times current. But for some reason, the quantum equations are written in terms of momentum, P equals h over lambda, and energy, E equals hf. This makes no sense. Doesn't it make more sense to also write the quantum equations in terms of force and power? Modified unit analysis, as outlined in this paper and in this video, does exactly this, leading to a language that is both logical and intuitive, where the quantum of force is used to calculate a force, and the quantum of power is used to calculate a power. Just think about it. It is the opinion of moi, the author, that by assigning the units of action to Planck's constant, h, Planck and company inadvertently attached a per second measure time to a per cycle energy unit, forever blurring the true nature of light. This may also explain why quantum mechanics can only be done statistically. Further investigation is suggested. In conclusion, in this paper and in this video, the force that a laser exerts on an object is derived from first principles using the logic of modified unit analysis. Although the intermediate units differ from standard unit analysis, the final result leads to the correct value and the correct units as expected. The purpose of this exercise was to demonstrate the validity of modified unit analysis and to corroborate the alternate interpretation of light as outlined in Planck's constant and the nature of light. So before I end this video, I just want to say one more thing. Mainstream physics often uses the excuse that because the numbers work out, then their interpretation must also be right. Because they get the right answer, they assume that their model is correct. Some may also be tempted to call my line of thinking numerology, but I have news for those people. All of physics is numerology. All of physics is numerology. In the video that I presented here and in my paper, I show that I get the right answer. I'm using a completely different line of thinking, but I get the right answer. So I must be right, right? In the days of epicycles, the powers that be thought that they had the right model because their numerology worked out. But they weren't right, were they?